The idea of d-star Lite is based on updating and reusing the previous results on the search, and it can be demonstrated in this video. So before we deploy the robot and follow the planet path, we assume that all doors are open. So we find the initial path, but then once we follow the path, we realize, okay, the first doors are closed, and then we replan, and then we realize other doors are also closed, and so on. So we first, okay, now we switch, and then we need to follow, and again here we will realize that's closed and replan. So if your planning algorithm is fast enough, you can repeat the planning first of all. But in most cases, you can speed up and save the computational time and actually perform in real time by reusing the results. And one of such algorithm is d-star Lite. D-star Lite is very similar in behavior to the d-star. It has the similar name, but it's actually based on lifelong planning A-star. It has been proposed by Sven Koenig and Maxim Likachev in 2002 in the paper published at AAA. AI, just highlight, okay, this is the forum where you can find such algorithms. So it searched from the goal node to the start node, so we are not searching from start to goal, but from the goal to start, using the G values that estimate the goal distance from start to the goal. And there is the priority queue used for the open list, so we store there pending nodes. And nodes are processed in order of increasing objective function. So we are greedy, we are focused on what is the most promising because that will be the shortest path. The main advantage is the ability to incrementally repair solutions once we are able to detect changes. So once we plan a path, we assume, okay, that this is open, so we pass through, and then we execute and we realize, okay, it's closed, so we update and repair the plan. And it is achieved by using two estimates costs. The G value, this is the objective function value, and RHS, this is one step look ahead of the objective function value. And using these two values, you can check the consistency. If both values are the same, so we consider it's consistent, and once not, it's inconsistent, and we can repair. And the inconsistent nodes are the nodes that are put to the open list. So once we will expand open list, it can be put back to the open list if we detect the change, because it will be inconsistent. So this Starlight cost estimate, RHS, one step look ahead of the node U, is computed using the G value of its successor in the graph and the transition cost between the edge of to these successors. So once we have a star, so it's 0, then we consider the minimum value of the successor. So we examine all neighborhood nodes and choose the cheapest one. This is the most current cheap path to reach the U, and we actually consider the priority or key value for the open list as a minimum of the G value and RHS with some focus on the heuristic H, and the GS and RHS. So these are the minimum values. This is the primary key, and the second term is used for type rating, but that's just implementation detail if you like to speed up the priority queue. So how's the Starlight algorithm working? We have the initialization. So we initialize all the grid or cost estimates, objective values of the war grid as infinity, so there is no known path, and we said that the goal is the distance to the goal is 0, and then we insert the goal to our open list U, and we compute the shortest path, which will be in the moment, and once we will not reach the goal, so we extract from the roadmap the next node to visit, and we move to it. And if it happens, so we continue. And if not, because there is, for example, detected doors in the closed doors, so we introduce these changes to the grid, to the graph, and update it, and compute the path again. So how it is the computation of shortest path. So once we have on top of our open list a key that is lower than the current start, or there are some inconsistencies in the start node, then we pop up a node from the open list, and then we can figure out if it is over consistent or under consistent or estimated. So if the current value of G is above the one step look ahead, then we update the G. So it's that's the shortcut, and we update the vertices. And if not, so it means that the G value is lower or equal than the RHS, then we set it to infinity and again update the vertex. And update vertex means that if the vertex U is not the goal, then we compute the R one step look ahead using the cheapest successor, and insert it to the, and if it's not consistent, we insert it to the open list. And this is just that how the keys are calculated, because we are using these keys. So this is a demo. Actually, you can, I guess, download it, but there is actually a small bug. It's not perfectly working unless the authors fix that. I believe that going through an example with very detailed description of the steps will provide you the background how the Lite exam works. So we'll start with this example. So we have this grid environment, and on top of this grid we have 8 neighborhoods. So we have this star, we have this goal. These are the cells. This is the first number is the row number, second number is this column number. These are the obstacles. So at the beginning, and we will have this scores and coding. So this is the actual map of the environment. So that's what we know. We consider diagonal edges are, so it's a bit longer, and the transition cost from to obstacle is infinity. So yes, starting. At the beginning, we set everything to infinity except the goal. So one step look ahead, we set to 0. So that's because we are finding a path from goal to start. We put the goal, the node with the set one step look ahead estimate to 0. We put it to the open list because it is not consistent, right? Because others are consistent because are both infinite. Now we call the compute shortest path. So we pop up the minimum element from the list, and it is over consistent because G is above the one step look ahead. So we set to G to RSH. So that's the true cost. We already searched for that now. And now we expand the other more labeled nodes. So we compute the one step look ahead. So we set it, okay, this is 1, this is 1. And these nodes become inconsistent. And this node for the diagonal is actually also expanded, but it is a transition to obstacle, which is infinity, which means that this is consistent. So we will not expand this. It's not put to the open list. Okay. Now we continue. So we pop up the minimum element. Let's in this case be this one. It's again over consistent. So we set up the G to 1. And we follow again. This is consistent because we move from free space to obstacle. This is infinity. And here we update the one step look ahead. So we have this G value 1 plus 1 is 2 and diagonal 2.4. And we put that to the open list. Now we will expand the open list. And we pop up the minimum node, which is this one. But this will be easy because it's already the obstacles. So we expand next one with the minimum value is this one. Sorry, that's it's 2 and 8. It's over consistent, so we update it to 2 and again expand. And here we can expand 3 plus 1 is 2 plus 1 is 3. 2 plus 1.4 is 3.4. 2 plus 1 is 3, so we will not update this one. But once we pop from the open list, so this is the minimum value. It is again over consistent, so we update it and expand. And here is the same, so we not update reaching this location using this node and update the other ones. Again, 1.4, 2.4 plus 1 is 3.4. Now the cheapest is this one. It's over consistent. We update, and none of the successors will be updated because it's already set up and will be the same or higher. So we continue now with this one, and we almost reached the start. We continue with this one. Nothing happened with that, so this is over consistent, and now we already put the start location into the open list, but we still have to process the nodes with the lower values, right? Nothing happened here. We expand this. We have now this one, and it is over consistent, so we set it and we are done. So optimal path is found, and the loop of the compute shortest path is break, and we can follow the path. So this is the start. We choose the successor or predecessor. This one, that one, and we will reach the goal. So this is once we have a solution, we reach the start. So we can follow the path. This is the gradient path. And we will make a step. Okay, nothing happened. Now we will make a step and we discover new obstacle. So we need to replan. We need to update the plan. So which basically means that we need to update the related neighborhoods. So this is no longer free space, it's obstacles, so transition cost is infinity. And what we need is to update the related nodes and nodes that for which the shortest path pass this new obstacle. So in this case, we are going to diagonally, but the same cost actually is for this the left neighborhood. So it will not change the estimates, but will change the successor or of the node. So we will continue here. We change, so we update the one step look ahead of the G value and perform the others. This is the same, so we update the one step look ahead, which is the G value plus 1. It's 5.4. Nothing happened here. So now we have this node as the cheapest node from the open list. It's under consistent, so we set it to infinity. And we update the neighboring nodes, right? So this one is the shortest path from this node is using this upper node. So 4.8 plus 1.4 is 6.2. We are not updating the G value. And same happen here. Okay. So what we have now is the open list that looks like this, and what is the cheapest node is actually this one, right? So we update it using the G value here. Because it's under consistent, we set the G to infinity. And the same actually happens for the neighboring nodes. And so was under consistent, the update vertex is needed. It's still inconsistent, so we are putting it back to the open list. And the cheapest now is this one, because the G is still infinity, but one step ahead is 5.2, and it is over consistent because the G is above the one step look ahead, so we can set the G, and we are done with this one, but needs to update the other paths. So we update the neighborhoods. But for now, we already have the shortest path, so that's okay, because that was our new start. So that was briefly the idea of the D-star Lite. And it actually happens, the changes happens through this one step look ahead and G value, and we have the under consistent and over consistent nodes. And once we have G is above the one step look ahead, so we can set it, because the one step look ahead is true value. And if the G is lower than one step look ahead, so we are not sure what is the shortest path, so we set it to the infinity, and then it will be popped up from the open list again once we update the related nodes. So let me put some comments. D-star Lite works with real value cost, not only with the binary cost free obstacle, right? So that you can put the cost of the transitions. The search can be focused with admissible heuristic, so that would be added to the G and the one step look ahead values, and the final version of D-star Lite, which is not shown in the example, actually needs some further optimization, and that is the updating of the one step look ahead value without considering all successors every time, because you can speed up it, and can refocus the search as the robot moves without reordering the entire open list. So that's some speed ups.